All right, everyone. Welcome to lesson 21 of Calculus 3. Today what we're going to do is we're going to have a review of polar coordinates from Calculus 2, and then we're going to generalize polar coordinates to 3 dimensions. And it turns out that there will be 2 common ways in which we're going to be doing that. Now, why on earth would we do this? Well, we just saw in the last lesson that we can integrate over arbitrary regions, not just rectangular regions. And as such, if we're integrating over, say, something with circular symmetry, it may be easier to express that in terms of polar coordinates rather than rectangular coordinates. So we want to be able to use that when we're looking at integrals over 3 dimensions, or 2 dimensions. So let's go ahead and review polar coordinates from Calculus 2. So suppose we have a point x and y, and we want to turn this into polar coordinates r and theta. How are we supposed to do that? Well, remember what r represents. R represents the distance here from the origin to the point, and theta is going to be this right here. So if we want to get x and y in terms of r and theta, then we use trigonometry. So if we have r is the hypotenuse and then this angle theta, then this vertical distance y will be r sine of theta. And then this horizontal distance will end up being x is r cosine of theta. So if you have x and y and you want to, or if you have x and y and you want those in terms of r and theta, this would be how you do it. Now if you want things the other way, let's say you want to get an equation for r and theta in terms of x and y, well remember we also have a triangle here. We're also going to use properties of the triangle. We have a leg y and a leg x and a right angle here. So by the Pythagorean theorem, this is going to be the square root of x squared plus y squared. And that will be equal to our r. Now in general polar coordinates, you can have negative r values. We've discussed what that meant in Calculus 2. But for our class, we're just going to restrict it to positive or 0 r values. So I'm just going to have the positive square root here. And then how will we get theta? Well, tangent of theta is going to equal the opposite over adjacent. So tangent of theta will be y over x. And if you like, you could also do theta is arctan of y over x. That also works as well. So anyways, that's these 4 equations here, this, and this, or sorry, this and this, form the different conversions between polar coordinates and rectangular coordinates. And they're summarized below here. So if you have polar coordinates and you want to turn them into x's and y's, this would be how you do it. You plug your r's and thetas into this side and you get out your x's and y's. Or if you have things in the other way, if you have x's and y's and you need to get r's and thetas, this would be how we do it right here. And as I said earlier, we're going to restrict r to be greater than or equal to 0 for our purposes. Alright, so let's get a little bit of review of polar coordinates going here. Convert to an equation in rectangular coordinates. So we want to get rid of any r's or thetas that we see and replace them with x's and or y's. Alright, so if we have r is equal to 2, remember that r is the square root of x squared plus y squared. And then if we square both sides, we have x squared plus y squared is 4. And hopefully we recognize this. This is the circle centered at the origin of radius 2. So we can draw that relatively easily over here. And you can already see the difference in the utility between polar coordinates and rectangular. So polar has a really simple form for this circle right here. It's just r equals 2, a circle of radius 2. But with rectangular coordinates, it's a little bit more complicated. We have to square both of them and add them together, and then we get the radius squared. So it is a bit easier to write circles in polar coordinates. All right, for our next example here, we have r is 2 cosine of theta. So what's going to happen with that? Well, what I'm going to do is I'm going to multiply both sides by r. So I have r squared is 2r cosine theta. Now, why did I do that? Well, I know what r squared turns into. It's x squared plus y squared. And I know what r cosine of theta turns into. It turns into x. So what I'm going to do now is I'm going to subtract this over. And then I'm going to complete the square over here. So if I divide this by 2 and square it, I get 1. So I'm going to add 1 to both sides. All right, so we have 1 like that. And then this will factor. So we have x minus 1 squared plus y squared is 1. All right, so then what is that telling us? This tells us that we have a circle of radius 1, but it's not centered at the origin. It's centered at the point 1, 0. So let's say this is 1, 0 right here. If it's radius 1, it just barely touches the origin and extends 1 in the other direction as well. Oops, it's a little too big. There we go. Another way of remembering this is that, remember, cosine goes in the x direction, and you can remember the coefficient in front of it as the diameter of your circle. So using the same reasoning here, we could do exactly the same algebra with sine. We would get x squared plus y squared is 2y. We would complete the square with that, and we would end up getting x squared plus y minus 1 squared is 1, using the same technique we did up here. Or we could have recognized that this 2 is going to be our diameter, and sine of theta, that represents the y direction. So we would draw our diameter 2 circle starting at the origin and going in the y direction like that. So this circle is going to be centered at 0, 1. All right, and then the final thing we have here is r is 2 cosecant of theta. Now this one's going to be a little bit different from the other two. This won't represent a circle necessarily. I'm going to multiply both sides by sine, so we get to the more familiar trig function. So we have r sine of theta, and sine times cosecant will be 1. So we just have 2. So r sine of theta is 2, but remember, r sine of theta is y. So we end up with a very simple equation that y equals 2. And what is that? That's just a horizontal line at the height 2. So now we see the reverse situation going on here. We have a somewhat complicated r and theta formula, but a very simple rectangular formula expressing something that is straight. So for straight things, we definitely prefer to do things in terms of rectangular coordinates. But in case we do need a line in polar, this would be how we would do it. Okay, so now we've converted from polar to rectangular. Let's go the other way. So now we have these equations in x and y that we want to convert into polar coordinates. All right, so we have x squared plus y squared here. Well, we know what that is. That's going to be r squared. And if we take the square root of both sides, and remember that we're letting r only be positive, r 0, r is going to equal root 5 here. So what is this? Kind of similar to the thing we had on the previous page. If we ever have r is some constant value, that's going to be the circle centered at the origin with that radius. So this is the square root of 5 right here. All right, and then here we have y is the square root of 4x minus x squared. Now this looks a bit more complicated. Let's square both sides, get rid of the square root. So we have y squared is 4x minus x squared, like that. All right, I'm going to add x squared over here. And I'm also going to subtract 4x over here as well. Okay, and then what I could do is I can complete the square with this right here. So if I divide this by 2 and square it, I get 4. So I'm going to add 4 to both sides. And then I'm going to factor here. And there we go. So we have y squared plus x minus 2 squared is 4. Now before, let's see here. Yeah, so this is going to be a circle centered at 2, 0. So let's say that's right here maybe. Now before we draw this, we need to remember that y was the square root of something, right? So that kind of secretly implies that y is going to be greater than or equal to 0. So we're not going to draw the entire circle for this. We're only going to draw a half circle like this. And how would we convert this into polar coordinates here? Well, that would kind of come about at this stage. So we have y squared plus x squared is 4x. This would be r squared is 4r cosine of theta, and then we would have that r is 4 cosine of theta. But we would add the condition that our theta is going to be in between 0 and pi over 2, it looks like. Yeah. So we need to restrict theta here because we don't want to go too far around the circle, because then we would start getting this negative part right here. So this would be our half circle right here, which is what this is describing. All right. Now let's try to describe the shaded region in terms of polar coordinates. Well, first of all, why don't we try to convert these into polar coordinates? That might help us out. All right, well, we have y is x, so y is our sine of theta, and then x is our cosine of theta. So assuming that r isn't 0, we can divide that out right here, and we have the angle where sine of theta is equal to cosine of theta. Well, that's going to give us that theta is going to be pi over 4. Now you might be like, okay, well there are other angles that do that, like 3 pi over 4, things like that. But remember, those will all just be lines pointing in this direction, whether they're facing this way or they're facing this way right here. So I'm just going to pick theta is pi over 4. So that's going to give me my diagonal line, and that's at an angle of pi over 4. All right, now what is this going to be? Well, if I turn everything to r's and thetas, I end up with this, and then if I cancel out an r, I have this right here. R is 6 cosine of theta. Now remember, this represents a circle of radius 3 centered at the point 3, 0. So that's what this is going to be. Now let's see here. We want to try to get the shaded region, right? So that seems to be everything happening above this line. So it looks like we want angles that are bigger than pi over 4, but then this whole thing stops at pi over 2. So I want my theta to be in between pi over 4 and pi over 2. But I can't just have any theta value like that, because then otherwise I would be able to go out here like this. I need them to be within the circle. So this is the boundary of the circle, but I need my r values to be closer than that, or the same distance. So that means that r is going to be less than or equal to 6 cosine of theta. So this is kind of hemming in my r's within the circle, and this is getting it so I'm only having circle values above this line right here. So that would be how we would describe this in polar coordinates. And this is an important skill right here. Make sure you understand this problem, because we're going to be doing a lot of converting regions from one type of coordinate to another. It's going to be a very common process that we're going to be doing when we do these integrals in the future lessons. All right, so that was all essentially a review of polar coordinates. So now what we're going to do is we're going to generalize the polar coordinate system, which worked in R2, to what are called the cylindrical and spherical coordinate systems that will be ways of describing points in R3. All right, so cylindrical coordinates. So cylindrical coordinates is what I consider to be more the simple way of extending polar coordinates to three-dimensional space. So normally we're accustomed to x, y, and z as a way of labeling points, right? So what we're going to do is, now that we know how to, or at least remember, how to convert our x's and y's into r's and thetas, we're going to do so. So we're going to use exactly the same conversion formulas that we used on the previous pages to convert our x and y into r and theta. And then we're just going to leave z alone. So effectively what's happening, let's say we have an arbitrary point in R3 here. What we're going to do is we're going to project that down to the z equals 0 plane, and we're going to see, or the xy plane, and we're going to see what its polar coordinates would be there. So here is our theta. Remember, theta starts at the x-axis and rotates towards the y-axis. So here's our theta. R is our distance from the origin to our point in the xy plane. So then once we identify our projection in the xy plane, then we simply just go either up or down however high we are. So this is going to be z right here. So effectively we just continue doing polar coordinates in x and y, and then we just tack on z as shifting either up or down. That's what we're going to be doing with cylindrical coordinates. So our conversion equations are exactly the same as they were for x and y to r and theta right here, and then we just have z equals z, because no matter if we have x, y, and z here, r, theta, and z, these z's are identifying the same thing. It's still going to be our vertical, how high up or down we are. So there's really no conversion necessary for z. And then same thing if we want to go from rectangular to cylindrical. Here's how we get r, here's how we get theta, but we already have z. So there's really no conversion equation, or no interesting conversion equation for that. All right, so let's get some practice with cylindrical coordinates. So we're going to describe the solid E in cylindrical coordinates rather than rectangular coordinates. All right, so E is all of the points x, y, and z such that x squared plus y squared is less than or equal to 5, and z needs to be between 0 and 7. All right, now let's also try to describe this in terms of r, theta, and z. So we're looking for all the r, theta, and z such that, and then we need to convert these conditions to r's, thetas, and z's. So we have x squared plus y squared. Well, that's a good place to start because that's going to be r squared. And then if we take a square root, we need r to be less than or equal to root 5. So we need that. And then the z condition can remain exactly the same because we use the same z that we used with rectangular coordinates. So what is this set saying here? What is the set of points? It's the set of points where your x and y coordinates need to be within a circle of radius root 5 away from the origin. So if we look in the xy plane, let's say we have 1, 2, and then a little bit for root 5, we need to make sure that all of our points in the xy plane are in this circle right here. And then our height above that we can go is from 0, anywhere from 0 to 7. So let's say maybe this here is a height 7. And since these are inequalities, we have less than or equal to, this whole thing would actually be filled in. And we would just have a cylinder of radius root 5 and a height of 7. Now, I'm sorry, my drawing isn't the best, but I'm attempting to draw a cylinder of height 7 and then radius root 5. So that's what this shape is going to be. All right, so we have that. All right, let's find an equation in cylindrical coordinates for this surface right here. All right, well, whenever I see a square root here, I'm always tempted to square it to undo it, but we need to remember that this is going to imply that c is going to be greater than or equal to 0, since we have a square root here. So we have z squared is 4x squared plus 4y squared. Well, what we can do is, upon factoring the 4 out of this, we see that x squared plus y squared is our familiar friend here. This will turn into 4r squared. And then finally, if we take the square root of everything, and it's going to be the positive square root because we need a positive or 0z, we end up with z is 2 times r. So what is this saying here? What does the equation z equals 2 times r mean? Well, this means that our height is going to be twice as far as our point is in the xy plane from the origin. So that means that the further we go in the xy plane, we're going to end up being twice as high. So for example, if we start at the origin, we're 0 distance away in the xy plane from the origin, our height's going to be 0. But as we move out, say, a distance 1 maybe, like let's say we go in the x direction a distance 1, we're going to go up to a distance of 2 here. And that's going to happen in any direction. Remember, this is just the general distance in the xy plane from the origin. So if I go the same way in y, I'm also going to extend up that way. And this is a linear relationship. If I go up 1 unit with r, I go up 1 unit with z. So that's why these are lines here. And it's not just in the pure x direction or pure y direction, it's in any direction. So what we end up getting is, since it's the same in any direction, we can effectively draw a circle right here. It's circular symmetry because we can go in any direction we want. And what shape does this end up making? This ends up making a cone. So this is going to end up being a cone, although remember, with our cones earlier, we also drew them extending in the negative direction, but we're not going to do so with this cone because z is the square root of a number. So we're only going to have the upper half of this cone. And this could go on indefinitely here, by the way. So this extends even further out like that. So we end up getting an upper cone here. All right. So that's cylindrical coordinates. That's kind of like the most simple generalization of polar coordinates. But now let's talk about spherical coordinates. And these are a little bit more complicated. We're not going to keep any of our original coordinates like we did for cylindrical. So in R3, a point P in the spherical coordinate system is represented by the order triple rho. So this isn't a P, this is actually a rho, theta and phi, where rho is the distance between P and the origin. So this isn't just the distance in the xy plane anymore. This is just the straight up distance all the way through space. So if we draw a line from our origin to our point P right here, the length of that will be rho. All right, what's theta? Now theta is the same thing that we saw in cylindrical coordinates. So if we drop this down into the xy plane, then theta will be this angle here. So it's the angle from the x-axis all the way out to how far our point is rotated towards y. All right, and theta can extend from 0 to 2 pi, so we can go all the way around if we like. And then phi is the angle formed by the positive z-axis and the line segment connecting this to the origin. So what is that going to look like? Well, we start at z equals 0, and then we rotate downwards towards the xy plane. And we're going to come down this angle, and then we're going to crash into our line segment here. So this angle right here is going to be phi. And the thing that trips a lot of people up about this is phi is only going to go between 0 and pi. Now, why is that? Why can't it, like, let's say we wanted phi to be 3 pi over 2. So we would rotate all the way like this, and then we would rotate over here. Well, that would be the same as if we rotated theta around this way and then had phi be less than pi, like that. So since we allow theta to go from 0 to 2 pi, it's unnecessary for us to allow phi to go all the way around like that as well. So phi only needs to go from 0 to pi to every possible point. And unlike polar coordinates in Calculus 2, where there are many different ways of representing the same point, for these coordinate systems, we're going to try to make it so that each point only has a single representation. So that's what we're attempting to do with these restrictions here. All right, now the conversion system is a bit more complicated since we didn't retain any of the original variables. Let's do some trigonometry here. So here's this rectangle, and it's sort of this diagonal plane that's rotated at an angle theta here. Now, if I use trigonometry, I have this hypotenuse rho and this angle phi, or phi, right here. So this vertical distance from here to here is going to be rho cosine of phi right here. Now, the vertical distance from the origin up to how high we are, that's none other than z. So z is going to end up being rho cosine of phi. All right, well, if this is rho cosine of phi, then this has got to be rho sine of phi. But if this is rho sine of phi, then that means that the parallel line down here is also going to have length rho sine of phi. Now, what we're going to do, we kind of shade this in a little bit. Remember, rho sine of phi, that's effectively what our r used to be with polar coordinates, right? So this is how far we are from the origin in terms of our x and y coordinates. So rho sine of phi is r. Now, how did we get x and y in terms of r? Well, remember, this right here, so this is how far we are in y, this is going to be r sine of theta. But in terms of what we have now, we start off with a rho sine of phi, and then we tack on a sine of theta. And then this is going to go the same way. This was originally r cosine of theta, but our r, remember our r now, is rho sine of phi. So we're going to have rho sine of phi cosine of theta right there. And that's how we're going to get our x, y, and z right here. Now suppose we want to go the other way. So suppose we have rectangular coordinates and we wish to convert them into spherical coordinates. How would we do so? Well, we can use the Pythagorean theorem to start to get rho. So rho is going to be the square root of x squared plus y squared plus z squared using the three-dimensional Pythagorean theorem. For theta, remember tangent of theta is y over x. And that's still true right here because theta is embedded in the xy plane here. So we have y here and x here, so tangent of theta will be y over x. Now cosine of phi, that's in a different triangle here, so it has hypotenuse rho and adjacent side z. So if we divide this equation by rho, we have z over rho is cosine of phi. And that's what we're going to be using here to get phi if we need it. All right. So now, just like we were describing regions in terms of cylindrical coordinates, we're now going to describe them in terms of spherical coordinates. All right, so we have x squared plus y squared plus z squared is less than or equal to 9, and all of x, y, and z are greater than or equal to 0. So this means that we're in the first octant here. All right, so this right here is saying that rho squared is less than or equal to 9, so rho is less than or equal to 3. Okay, so when we make our new set, rho, theta, and phi, we're going to have rho is less than or equal to 3. Now, how do we get these conditions in here? So this just means that we're in the first octant, right? So if we consider theta, we can only rotate around this much, right? So if we rotate any further, we'll be out of the first octant. So theta seems to be restricted between 0 and pi over 2. Looks like I ran out of room there. Let me go here. And then phi, if we start from the top down, that also seems to be restricted to pi over 2. Because if I rotate down any further, I'm going to have a negative z value. So that will also be restricted like this. So there we go. Now we've been able to turn this into spherical coordinates. Now what is this representing? This is representing 1/8 of a filled-in sphere. So we have x squared plus y squared plus z squared is less than or equal to 9. So this means that we're within a sphere of radius 3, but then we're also within the first octant. So if we wanted to shade this in, it would be like this. So it would be 1/8 of a sphere. It would be the sphere of radius 3 centered at the origin that's in the first octant. So sphere of radius 3 centered at 0, 0, 0 in the first octant. That would be how we would verbally describe this. All right, let's try something else. Describe the surface Z equals the square root of x squared plus y squared in spherical coordinates. Now we actually already saw what this was in cylindrical coordinates. This ended up being a cone, or rather an upper cone. So let's see how this ends up working out with spherical coordinates. Let's see what the cone equation looks like there. So let's see here. Let's square everything just like before. So if we square everything, we get this. Now what I'm going to do here is I'm going to turn everything into rhos, thetas, and phis now. So remember, z is rho cosine of phi. So then we're going to get rho squared cosine squared of phi. Meanwhile, over here, x is going to be rho squared sine squared of phi cosine squared of theta. And y will be the same, only we're going to have sine squared of theta as well. Now, look at what we have here. This is always our favorite thing to have happen with these trig functions. We have a cosine-sine Pythagorean pair. So if we were to factor this, then this is a very fancy way of writing 1. So that means that we have the equation rho squared cosine squared of phi is rho squared sine squared of phi. All right. Well, if we cancel out the rho squareds, We have cosine squared of phi is sine squared of phi. Well, let's see here. What angle will cause this to be true? Well, that's going to give us phi is pi over 4. Now, why didn't I pick phi is 3 pi over 4? Because that also would have worked with this. Well, if phi is 3 pi over 4, that's going to give us some negative z values. And remember, we don't want those here. So we're just going to do phi is pi over 4 for this. So if we do phi is pi over 4, we're just drawing diagonal lines in any theta direction. So theta can be any value that we want, and we're going to end up getting our cone right here. I guess I should draw it a little bit more like this. There we go. That looks a little bit better. But yeah, so our equation for this is simply going to be phi is pi over 4. Now, if we allowed z to be negative, then phi could be pi over 4 or 3 pi over 4. We would have to include that as well. But since we only want the upper part of this, we're going to have phi is pi over 4. Now notice that there's no restriction on rho, so we can go as far away from the origin as we want, and there's no restriction on theta, so we can rotate around in any direction. The only restriction is that we need phi to be pi over 4. All right. So let's see here. So we're going to identify the surface r equals 4 sine of theta in cylindrical coordinates. Well, the interesting thing about this is that there isn't any z value. All it's saying is that r needs to be 4 sine of theta, and that's talking about the xy coordinates. So if we draw this in the xy plane here, remember this is a circle of diameter 4 in the y direction. So if we draw such a circle, maybe it looks something like this. Here is our circle, r is 4 sine of theta. Now notice that they didn't say anything about z. Now this ends up confusing a lot of people, so let me explain this carefully. If they don't say anything about a coordinate, then that coordinate can be any value you like. Kind of like the previous example, actually. If we look back here, we can be any distance we want from the origin on our cone, and we can be any angle theta we want because we can rotate in any direction. So just like they didn't specify rho and theta back then, they haven't specified z here. So z can be theoretically any value you'd like. So that means that we can go up any kind of z value as long as we're still sticking to being on that circle with our xy coordinates, and then we can go down by the same amount. So we end up with a cylinder of radius, I guess it's going to be 2, centered at the point 0, 2. So this is going to be our cylinder here, and since they didn't specify what z is, z can be any value whatsoever. We just need to make sure that we're lying on the circle. All right. Let's identify the surface. Rho is 4 cosine of phi in spherical coordinates. All right, let's see. Now I know rho cosine of phi will be z. So that kind of tempts me to multiply both sides by rho here. So I have rho squared is 4 rho cosine of phi, meaning that rho squared will be 4z. Remember, rho cosine of phi is z. Now, rho squared, on the other hand, is x squared plus y squared plus z squared is 4z. Now, what I'm going to do is I'm going to subtract this over, and then I'm going to add the magic number, or divide this by 2 and square it to both sides. So we have x squared plus y squared plus z squared minus 4z plus 4 is 4. And then if we complete the square here, then we end up with this. And what is this right here? This is going to be a sphere of radius 2, but it's not going to be centered at the origin. It's going to be centered at the point 0, 0, 2. So let's say that point's right here. We end up having a circle in every possible direction here for our trace. Well, this looks a little bit more like an ellipsoid, but I think you get what I'm saying here. This is going to be a sphere of radius 2 centered at the point 0, 0, 2. So whenever you see a trig function on its own without a rho or an r in the case of cylindrical coordinates, it pays to just multiply both sides by that so you can turn this into a rectangular variable. All right. Let's see here. I think we have 2 more examples of this. Sketch the solid described by the given inequalities. All right, so since they're using r's, we know this is going to be in terms of cylindrical coordinates. So on the one hand, we have z is greater than or equal to r squared. Well, let's see what z equals r squared looks like. Oops. There we go. So what z equals r squared looks like is the further we get away from the origin in terms of our x and y coordinates, the square of that distance is going to be how high we're going in z. So if we extend linearly in the x or y or some combination of that direction, we're going to increase quadratically with z. So that means that it's going to look like this if we go in the x direction. It's going to look like this if we go in the y or in the negative x direction. Here's positive y. Here's negative y. And remember, it doesn't matter which way we go. We can go any combination of x and y. It's just that the further out we go, we're going to increase quadratically. So it ends up being this, and this is actually a paraboloid. All right. Now next, or elliptic paraboloid. Anyways, next we have z is 8 minus r squared. So what this means is that we start at a height of 8, which maybe is up here, and then we decrease quadratically the further we go with x and y. So I'm going to extend down like this, and like this, and like this, and like this. And I end up making this sort of sphere that's kind of quashed a little bit and ends up kind of intersecting at this sharp angle here. The analogy for this is back in R2, let's say we graph the equations y is x squared and y is 8 minus x squared. Y is x squared looks like this, but then 8 minus x squared would just be an upside down parabola, and they would intersect like that. So it ends up kind of looking like a circular eye shape, I guess. So that's the best I can draw it here, unfortunately. But that's what this is going to end up being like, because all of the z values are going to be everything in between. So this is going to be a filled-in kind of eye shape. So it's like this. This would be a cross-section of it, and then it would be rotated around the z-axis. All right, and finally, let's do another one with spherical coordinates here. So we're going to sketch the solid described by the given inequalities. So rho needs to be less than or equal to 1. Our phi needs to be between 0 and pi over 4. And our theta needs to be between 0 and pi over 2. All right, so let's take a look at each of these. So our theta restriction has us in here. So this is theta between 0 and pi over 2. And then our phi restriction, so phi is 0 is like that. Phi is pi over 4 is like this. And we can go in the y direction as well. So we can come down like that, and then down like this, and then we can rotate in the theta direction here. And then remember, our rho is less than or equal to 1. So let's say this distance here for all of these is 1. So what does this give us? This gives us a chunk of the sphere in the first quadrant. A sphere, I guess I should say, of radius 1. Now, it doesn't give us all of the sphere in the first quadrant. To get all of the sphere in the first quadrant, we would need this to go from 0 to pi over 2. So we would come all the way down here. But this is going to be kind of a piece of the top of the sphere right here. That's what this is going to end up being right here. All right. Anyways, so that's our introduction to cylindrical and spherical coordinates. And now next class, what we're going to do is we're going to learn how to convert our integrals from rectangular coordinates to cylindrical or spherical coordinates, which should make them easier to do in particular situations, like especially if we have any kind of cylinders or spheres or circular symmetry or anything like that, it would definitely be a good idea to convert to one of these new coordinate systems. All right, so that's it for now, so I will see you guys in the next lesson.